Good morning, everyone. I'm Piergiorgio, and I'm presenting a work on continuous orchestration of web services using planning techniques. Joint work with Raman Casamakin, Marco Pistore, and Georgi Reich, also from FBK Institute in Trento, and Massimo Paolucci and Matthias Wagner from Docomo Eurolabs in Munich, Germany. So, briefly, this is the talk outline. So, I will start by stating what is the service composition problem, in general and in our case. Defining what is the state of the art in composing services and discussing some current issues there before going into our contribution, which is allowing the continuous orchestration of stateful services. We will provide a planning-based solution for this. I will describe some experimental evaluation and then go on to conclusions and future work. So, what is service composition? Let's state informally the problem. What are services? Services are ways to expose, let's say, pieces of software through the web by means of standards. There are different standards available. And this is for the sake of reusability, essentially, of these pieces of software and composability. In fact, one interesting thing that you can do if you have services is to build new services on top of them using the existing ones, right? So the problem of service composition has as input a set of pre-existing services which has been exposed and some requirements that describe the new service that you would like to build reusing those services. Then, ideally, you fit this into a magic box service composition tool that produces a new service which was not existing before and which you can deploy and execute. And the execution of this service will speak with the other pre-existing services to realize your formal requirements, okay? This is a very general statement of the problem. And service provision is very interesting for a lot of stakeholders, like, for instance, for telecommunication companies. This is why it's an important market, okay? This is why people from telco work with us at this kind of problem. And if we are able to requirements that you want to take into account. What we deal with is stateful services, that is, services exposed by a standard called BPEL. BPEL is a language, an imperative language, which allows for asynchronous communication as well as synchronous communication. It has the usual imperative constructs, so sequencing, decisions, loops, so on and so forth, assignment on variables, these kind of things. So you can see that as protocols exposed as sort of programs. One interesting thing of BPEL is that you can expose protocols in an abstract way. What does it mean in BPEL terms, abstract BPEL? It means that certain points of the protocol that you expose can hide the implementation. Like, for instance, there can be a decision point where you say, OK, I will go left or right. The protocol will go left or right. But how the decision is made, it is opaque from the people that gets this protocol description. The reason for this is that business entities that expose these kind of protocols do not really want to disclose their internal procedures. Like if I go to a bank, I ask for a loan, they may say yes or no. Maybe they have some strange rules to do this, but they don't want to expose those rules. They only expose the protocol, right? So in this sense, BPEL protocols, abstract BPEL protocols are some sort of non-deterministic, not fully controllable, and not fully observable machines. Now, to compose this kind of services, you need to have requirements that speak both of data, so the way the data is routed during the composition, and control. That means what kind of logical behaviors do we want to enact by the composite services that act as an orchestrator, okay? So these are the input to our problem, and our output, again, must be a BPEL service that is a stateful entity, which in general may contain decision point and loops. So in a way, we are close to program synthesis, right? One example that is used to show this kind of problem is the virtual travel agency example, where essentially you start by admitting that there are a couple of existing services. Flight company offers booking service. Hotel offers you reservation service. You want to offer to a customer a protocol that combines the two so that he can organize a trip without having to speak one by one in person, okay? So you start from this description of protocols, and then you obtain this protocol in the middle that orchestrates these existing protocols. And what happens is that, of course, the control requirement here should say that only certain behaviors are good. Like, for instance, if you ask for a flight, but the flight is not existing, it's pointless to ask the hotel for reservations, vice versa. You have to keep the synchronization of the things into account. Now, when dealing with this kind of composition of stateful services, what is the state of the art? Well, the state of the art is this. Beeper services are very interesting, very relevant, it's good market, whatever, but they're difficult to deal with because essentially we are composing some sort of programs to obtain some other sort of programs. That's very difficult. So there are few approaches that consider stateful protocols, and actually the next talk will be also on another of the very few approaches dealing with these stateful protocols. Expressiveness. Well, regarding your service, the service that you want to compose, you want to say expressive things about the behaviors that it should enact and the way it composes the data from the services. Current approaches, in many cases, fail to be expressive enough because, for instance, they deal with pure reachability in terms of the kind of composition requirement that you may have. So you only can say, you have to compose these services and get to a final situation where everybody is happy. Okay? In terms of usability also, if we want to enable engineers, not planning experts, to use these kind of tools, requirements must be easy enough to write, okay? In some cases, this is not the case because you can see that they need logician skills to be used, current languages. Now, what do we want to do here? What is the contribution of this work? We want to be able to deal with these kind of scenarios which are appearing more and more and which are really interesting, where essentially you do not need to just synchronize services and get to a certain situation and then you're done, you're happy with it, but there exist services which proactively cause events to which you need to react, and the reaction is not trivial. For instance, nowadays when you book a flight, you're happy. In principle, you can book the hotel and you're happy, but then Lufthansa will send you an SMS on your cell phone or an email saying that the flight has been delayed or canceled. Okay, so you have to be careful, watch for those notifications, and react to this. Reaction can be non-trivial in the sense that, for instance, the flight is delayed, you have to look for a different day of booking the hotel, so you have to recontact a service which we were contacting before, see if realignment is possible. If this is not possible, you have to fall back, for instance, deleting all the kind of things that you did before, right? So what I'm saying is that in these scenarios, you need to keep the systems, the pre-existing services synchronized in a non-trivial way. And we want to do this, allowing this by some sort of expressive requirements, which should be fairly easy to write in any case. So let's take this as our reference example for the time being. And these will be then the protocols that enter into game. Now the question is, what are the requirements? Well, what we would like to require in that case is, well, first of all, you should book a hotel and a It's the Lufthansa that decides this, right? If the flight is canceled, you have to react and delete the hotel if you book the hotel. Even worse, every time that Lufthansa sends you an SMS and saying, look, the flight has changed, it has been postponed by 1 day, for instance, or something like, you have to check whether this needs realignment on the other services. That is, you have to check whether the other reservation is still okay, change it if needed, and if it's not possible to change it, fall back into a less desirable situation where at least you have everything canceled, okay? You don't leave your booking pending, okay? How we do this? By a simple control flow language, which is expressive enough, but it's still simple, which speaks about maintenance of criteria sorted according to user preferences and triggered by some events. Let's see. So, okay, this is the language. It's very easy. You have a clause on the left and a list of clauses on the right. And the clauses describe, in a way, either configuration on the states of the services or events, actions that the services have done, okay? Have done means that either they took the decision to take the action, like the flight notification service decides to send you a notification, or you force that an action causes. The meaning of this writing is, whenever the clause on the left happens, you should reach the clauses on the right. You prefer to reach the first one. If that is not possible at some point, then you fall back into the second one, the third one, and so on and so forth. Okay? So this is the high-level meaning of this kind of clauses. For instance, in our case, what we might say is the following. Look, if the flight status notification sends you a delayed message, this is an event that service has caused, then you should tell to the client that things have changed, and to the hotel that things should change. Similar for deletion, okay? These are not the only requirements that we need, of course, but this is an example. Now, how do we understand this kind of requirements? We can understand them in terms of automata, okay? This is probably not immediate, but a single requirement is converted into a hierarchy of automata. With the other automata, and you get to these acceptance states here. So essentially, you have these automata plus the other sub-automatas that run, and you have a list of acceptance states which are ranked according to preferences. So here, this acceptance state is better than this because it corresponds to the first clause, and this corresponds to the last clause, for instance. Okay? So how do I understand this sort of requirement? Is a set of automata synchronized among each other, which have some acceptance states, and those acceptance states are ranked according to preferences. What happens if I have more than one requirement? Well, I will have different sets of these automata. This is not a problem. They just run in parallel, okay? And I will have different lists of acceptance state, which I need to combine. This is not difficult to do. It's a sort of flattening procedure where you consider the combination of preferences, okay? So I will not enter in detail here, but once we understand the requirements in that way, how can we solve the problem using planning techniques? Well, essentially the idea is that those requirements together with the component services form a domain which we should be able to control. So also the services can be understood as abstract, as automata. In particular, there are automata which are partially observable, not fully controllable, right? So what you can do is translate those services into domain, and so what we do is we convert it into a fully observable domain, which still takes into account the fact that there are exogenous actions which you cannot control. So there is a transformation here by a belief level construction, and then once you have this domain, really, as showed in some previous papers, you can solve this kind of problem by planning for this domain, okay? The plan that you obtain is a plan that in general should have loops, should have decision points, and can be easily converted back into an automaton and finally as BPL. What we want really is start from BPL and get to BPL. So, but these parts of the translation are not, let's say, the heart of the problem. Now, conceptually, this approach might look similar to, is conceptually close to what we did in ICAPS 4 years ago for applying planning techniques for composition problem, with two main differences. First, there we consider some simpler goals which were not converted into automata. They were directly fed into the planner. And second, and more relevant, here, these goals must be understood as preference-listed configurations that should be reached and continuously maintained, because there are these exogenous events that trigger the fact that the automata exit acceptance states, and you have to act to go back to acceptance states. So these are the two differences, okay? And the fact that there is this difference in terms of how the planner shall solve this goal means that we need a new algorithm. How the new algorithm works? At a high level, it works in two big phases. So here we have two problems, dealing with reaction and with continuous alignment of services and dealing with preferences. In the first phase, just forget about preferences. We consider all the possible configurations of goal, and we try to identify which are the good states, meaning states by which, even if there is some exogenous action, I know that I can react and go back to some goal, okay? No matter what the preference. This will be a set of states, the only set of states on which we are really interested to search, okay? Now here, I have these states and I have to identify for each of these states which is the best action that I want to do to get to the goals according to my preferences. This is done by starting from the least preferred goals and building state action tables that say, if you want to reach that goal, you have to do this. So you start from the least preferred one, in this case, the goal number 3. Why is this? Because when you compute the state action table for a goal, the state action table for the worsened goals can be used as backup solutions, as we will see. So you really need to go in that order. And yet of this, you will have a coverage. So for each state, you will have at least one action that tells you you can do this. But in some cases, you will have more actions, some pointing to a goal and some pointing to a different goal. And you have to resolve this. This is very easy because essentially you have to transform this coverage into a partition following the layering that is mutuated by the preferences. So you have something like that then. Okay? So here, for these states in the middle, you don't know whether you can go to, you know that you can go to this goal, and of course you prefer the action that leads to this because it's preferable. With very, very few detail. So the first part of the algorithm essentially is a greatest fixed point algorithm that just removes bad states. How do you find good states? Keep removing the bad ones. The bad ones are the ones that either go out of your current set of good states because there is some exogenous action that leads you out, or which are not guaranteed to lead to some goal. This is a pruning, and that's it. The second part of the algorithm is more complicated. For sure, I will not show the algorithm, but the key idea is that of weakening. So weakening means when you look for actions that lead to a goal, first of all, you try to consider, you really try hard to go to the goal. So you consider only those states for which you are sure that you'll go to the goal. Say that you want to go to the red goal first. This is your preferred thing. So this is good, this is good, this is good. Now what do? Here I'm stuck because essentially I'm not sure. If I do this action, I can fall here. At this point, I have to weaken, to relax my assumption and say, okay, I admit that in some cases I give up this very good goal. I can go to less good goals, even though, I mean, the important thing is that I still have a chance to reach that good goal. So here I weaken, and then you can proceed with strong steps, and then you weaken again. So it's an alternation of trying very hard to get a point, and then when you cannot, you give up and relax a little bit. Algorithms, no way. So just a little simulation on a graph that I made up, where the red arcs are the actions that you control, and the green arcs are the actions you control, and the red ones are the ones you do not control, the exogenous events. So first of all, in this domain, you find the good states, you remove the other ones, then you start the search. Here you have the goals. The preferred is goal number 1, then 2, then 3, then 4, then 5, then 6. So here you get stuck. The interesting bit is when you get stuck at goal number 3, you realize that if you weaken, really you can consider also these states. Then you do the same for goal number 2, then you do the same for goal number 1. At this point, you're happy, and you merge the action. And for instance, at this point, you see that there is an action that is associated to goal number 1, an action associated to goal number 5. Of course, you pick the better one. That's it. So we implemented the algorithm symbolically using BDDs, and we tested first on our evaluation on our example, the extended VTA. I don't show you the people which is extracted. I show you the protocol which is extracted, okay? Which is this. And the interesting part bit is that you can really see what are the parts that take care of some bits of the requirement. Here is the creation of the trip. Here about what happens if Lufthansa tells you that the flight is deleted. Here is what happens if Lufthansa tells you that the flight has been delayed. These are connected, of course. As you can see, there are loops and decision points inside. So we really synthesize this, and this people has about 50 activities, so it's not really trivial. And we managed to do this in 35 seconds, so it's decent time for this kind of scenario. Some scalability tests on the number of services, number of goals, and number of preferences inside a goal show that preferences are really not a problem. If one digs into the algorithm, it's pretty clear why. Number of services and goal, they start polynomial, they are not really polynomial. Nevertheless, we really get to interesting kind of scenarios, relevant ones. So, conclusions, fast. What is service composition with stateful services? It's very relevant and challenging. However, it's complex because we deal with these stateful, asynchronous, non-controllable entities. You need expressive requirements, and you really need advanced planning techniques to deal with this. What we do here is we provide a simple language for expressing control requirements in terms of maintainability of condition and preferences. We have a new planning algorithm that supports this, and we implemented and tested. And the evaluation is fairly promising, I would say. Issues. Now, one big issue is requirements should be usable by engineers in a way. Now, so far, this kind of requirement that I showed you are tailored, are linked to really the services which are exposed. Is this good? Probably not, because if you change the service, if sometime I want to use not Lufthansa but Alitalia for some strange reason, then I would add, maybe Alitalia has a different exposure of the service, and I would have to rewrite the requirement accordingly. How do you solve this? You don't speak really of services. You have to think of higher level entities which represent logically the behavior of a flight booking system. Okay? And you should link these requirements to those high-level business objects, not really to services. This we did already. We have some work done, which has been published at ICAPS, which may be of interest. The other issue is are these requirements enough? It looks quite natural to say that if an event happens, then I may want to really do some steps in a procedural way rather than declarative. So we are thinking of, could we inject some more procedural requirements in our language? Would it be useful for somebody who wants to write things? Probably yes. So one can consider some sort of HTN form of requirements injected there. Not trivial to do, but if one can consider this mapping into automata again, can be doable. I never said a word which I heard so many times, which is heuristics, but I say here, of course, the issue is improving scalability. Heuristics is a possible answer. They are very hard to deal with, to introduce here, because they interact with a number of other things. You have loops, you have branches, and you have preferences. So this interaction between preferences and heuristics in this complex setting is not a trivial thing to solve. So I would say that's it. Okay.
Oh, sorry. So why actually, is it really required to plan ahead of time for unexpected events like this? Like why not do FF pre-planning, right? Something that happens.
Well,
because planning is hard for these processes already.
Yes, but the thing is, depends the way you want to use the composed service. Like for a business company, for instance, it can be useful to propose a service and to maintain the service in time. Like if some component changes, you have to rebuild it, and to implement it. Like you have, what you do is you do this composition ahead of time. You put it on your cell phone. You give it to the user. Then you say to the user, now you're happy. When you have to book a flight with me and the hotel with that company, run that service, it will do it automatically, and when I send you the SMS, it will tell you that something is wrong and blah, blah. So.
I wanted to know, is the problem you look at on the planning side when you have generated all the automata, is it more like a game that you play with outcomes at the end? So you might be looking also in general game playing specification and to decide that?
It's very related to game. In fact, I think that the next talk will show that these kind of problems are also close to game. Yeah, there is a close relation, and One thing which is there is preferences. So one have to look with games where you win if you satisfy something according to a list of preferences. So, but yes, it is related for sure.
So it's a non-zero game in the sense.
Yeah, maybe, yeah.
You mentioned the difficulty of writing the specification.
Mm-hmm.
You found a satisfactory solution for that?
Sorry?
Have you found a satisfactory solution?
No.
Can non-experts write those?
Well, yeah, let's say the solution could be, I mean, it looks like it is satisfactory if you write requirements that speak of higher level objects. So in higher level objects, you can speak more conceptually, rather than saying the message number 1. Yeah, because now in the requirement, you should say message number 1 of this service should trigger blah. So either you are an expert of that service or, but if you are an expert of the domain, you can speak about concepts, and that is easier. And then you have, of course, the problem of linking this high-level automaton to the low-level automaton. That's no. So what we did is preliminary. We have some work done at ICAPS. So it's in the methodology. So we have some work done. Yeah.
So I think we'll stop this talk and thank the speaker again.
Thanks.